Okay, good morning. You're joining with the missile paper number 4 MCQ discussion. There are 10 MCQs. The first round, this is made from the 2025 A-level paper. So there are 10 questions taken randomly from that paper. So let's discuss the first one. In acidic media, H2O2 can act as an oxidizing agent and reducing agent depending on the species it reacts with. That's correct actually. H2O2 can act as oxidizing agent as well as a reducing agent depending on the media. So that's correct. The next one, out of the oxidation states, oxygen exhibits zero and is the most stable and abundant. I am doubting that because water is there. Water covers majority of the earth, oceans and everywhere. Like it's the most stable form of oxygen where oxygen has a -2 oxidation state. Now you might argue with me, yeah, what about O2? O2 is also very stable, right? But more than oxygen, water takes more stability because oxygen is -2 and it has a noble gas configuration, right? Oxygen is 2 minus, so it has a noble gas configuration. We have to go with H2O there, so this statement is wrong. And answer is answer number 3. Second one, which of the following statements is correct regarding hydrogen halides? Hydrogen halides are acidic in water. That's correct. They will release H plus into the medium, which makes them acidic. Bond dissociation energies of hydrogen halides decrease when going down the group. Bond dissociation energies of hydrogen halides decrease when going down the group. When going down the group, bond length increases and the bond becomes easier and easier to break. When the bond becomes easier and easier to break, what will happen? Bond dissociation energy will decrease. So that's correct. Acidic strength of hydrogen halides decrease when going down the group. Actually, acidic strength will increase when going down the group, except for HF. Now, HF is a weak acid. It's a weak acid and it forms hydrogen bonds. That's why it's a weak acid. It will struggle to release the H plus properly. So that's why HF is a weak acid. Right. So we can tell acidic strength of hydrogen halides decrease when going down the group. That's wrong, right? That's wrong. Some people have taken it as correct with relation to HF, but actually when going down the group, acidity increase because when the bond length increases, when the bond length increases, it will become easier and easier to release the H plus. Then part D, bond length of hydrogen halides decrease when going down the group. No, when atomic radius increase, the bond length will also increase accordingly. So here we can go for answer number 1. Question number 3, that's a calculation question. I'll leave it to the end. Fourth one, which of the following statements is or are correct regarding S block elements? Right. The metallic radii of group 2 elements are less than the metallic radii of corresponding group 1 elements. Metallic radii of group 2 elements are less than the metallic radii of group 1 elements. Yes, that's correct actually. When going across the group from group 1 to group 2, size decreases. This is correct. B, first ionization energies of group 2 elements are greater than the first ionization energies of group 1 elements. That's also correct. So part C, the densities of group 2 elements are lower than the densities of group 1 elements. So when going across the group, size decreases, mass increases. Density equal mass over volume. So mass increases, volume decreases, therefore density increases. So this statement is wrong. Then part D, group 2 elements have weaker metallic bonds. Now that's wrong. There are 2 electrons delocalized into the electron pool. So therefore, the strength of metallic bonds is larger than group 1. So there you go, answer is answer number 1. Right. Fifth one also I'll leave it. Sixth one, VO is a basic oxide while V2O5 is an acidic oxide. That's correct. Right. So vanadium, chromium, manganese. Vanadium, chromium, manganese plus 4 plus 3 plus 4. Right. So these oxidation states are amphoteric. Any oxidation number below that will be basic. Any oxidation number above that will be acidic. Right. So here VO is a basic and V2O5 is acidic. That's correct. In Mn3O4, manganese is present as in a mixture of manganese 2 plus and manganese 3 plus. That is correct. Right. It's a mixture that is formed. Right. It's a mixture that is formed. When ammonium chloride and ammonium hydroxide are added to an aqueous solution containing Fe3 plus and cobalt 2 plus, only Fe3 plus precipitates. This statement is correct with regard to the cation analysis group 3. Fe3 plus is the only one who's going to precipitate because the OH minus is very less. right? The OH minus is very less. So we can take that as correct. White precipitate formed on addition of dilute NaOH to zinc chloride is insoluble in dilute HCl. Right, that's wrong. The zinc hydroxide will react with dilute HCl. Zinc hydroxide will react with dilute HCl. That's wrong. The first 5 elements of 3D transition series achieve their maximum oxidation by losing all 4s and 3d electrons. Yes, that looks correct. Right, that looks correct. First 5 elements, even manganese will remove all the electrons, right? Manganese +1 oxidation state, sometimes it forms. So this statement looks correct. So I'll go for answer number 4. Right, I'll go for answer number 4. Question number 7, 8, and 9, all are calculations. I leave it at the end. Then the 10th one, the correct order of increasing electronegativities of carbon in the chemical species C2, CH2, Cl2, CH4, COF2, and CH2F2. Let's see. Right. So CH4, C2H2, not C2H2, CH2Cl2, and then CH2F2, and then COF2. Right. In these compounds, this is going to be sp2 hybridized, right? The carbon atom is sp2, this is sp3, sp3, sp3. Hurry. So here the oxidation number will be -4. Here the oxidation number will be minus, minus, plus, and plus. That's going to be 0. Here the oxidation number is plus, plus, minus, minus. That's also 0. Here the oxidation number we don't need actually because sp2 is more electronegative. So we have to compare these three. Right. So among that, CH4 has the least because that has the lowest oxidation number. So let's select an answer. COF2 is the highest and CH4 is the least. Right? COF2 is the highest, CH4 is the least. Okay. We can go for an answer actually. Right? We can go for an answer. Answer is answer number 1. Right? COF2 is the largest and then finally CH4. When you compare these two, I'll tell it I'll tell this one also. Fluorine is more electronegative than chlorine. Fluorine will withdraw more electrons from carbon than the chlorine. Therefore, carbon has more positive, although the oxidation number is equal. The carbon becomes more positive in CF2H2. So therefore, actually the correct variation is this one. Okay, good. Let's go for the calculation questions. There are 1, 2, 3, 4, 5. There are 5 questions to do. Let's see. Third one, the enthalpy change delta H for the reaction given below at 25 degrees Celsius is minus 126 kilojoules. The delta H, this should be per mole. Maybe it's a mistake, right? Minus 126 kilojoules. Delta H for the reaction given below. They have given delta H. Delta H is enthalpy change, that is kilojoules per mole. Hurry, let's see. 2Na2O2 plus H2O goes to sodium hydroxide and oxygen. Right? So which of the following statements about enthalpy change is so are correct when a given amount of Na2O2 is added to excess water? Hurry. So 63 kilojoules of heat is released when 1 mole of Na2O2 is added. Okay, now this one is 2 moles. So 2 moles of Na2O2 is added to 2 moles of H2O to form 2 moles of sodium hydroxide and 1 mole of oxygen. Under these conditions, the enthalpy change is going to be minus 126, right? Under these conditions, the enthalpy change will be minus 126. So if you divide the number of moles by half, that means the enthalpy will be also halved, right? So it's going to be 63 kilojoules of energy is released. That's correct. Then part B, 31.5 kilojoules of heat is absorbed when 39 grams of sodium oxide. So 16, 16, 32, I'm calculating the molar mass. Sodium is going to be 23. 23 and 23 is going to be 46. 6, 7, 8, 4, 5, 6, 7, 78 grams per mole. Right? So the number of moles will be 39 grams divided by 78 grams per mole. Right? That's going to be 0. What is 39 divided by 78? 39 divided by 78. That's 0.5, right? Easy. 0.5. So 0.5 number of moles of sodium oxide is reacted, right? 0.5 moles are reacted. So actually, what's the total amount reacted to produce 126? That's 2 moles. So here 0.5 moles. So you have to divide that by 4, right? So this is correct. The only thing is this is absorbed. It's not absorbed, it's released. So minus, so it's exothermic. So this is wrong. Absorbed also wrong. 31.5 kilojoules of heat is released out. That's correct. Answer is answer number 4. Right? Answer is answer number 4. Very good. Nice. Right, we are going on to the next question. Question number 5. I'll take it to the screen. Manganese fluoride can be prepared according to the following reaction. If the percentage yield is 80%, what is the mass of MnF3 obtained when 0.1 moles of MnI2 are reacted with excess F2? Hari, 0.1 moles of MnI2 is reacted. Hari, if the percentage yield is 80%, percentage yield can may reaction nega karate, right? If you do this reaction, the yield is going to be 80%. That means the may value obtained mass divided by theoretical mass. Theoretical mass is what you get by calculation. So let's calculate the theoretical mass here. So number of moles of MnI2 reacted will be 0.1 moles. So number of moles of MnF3 formed will be how much? Same thing, right? 0.1 moles. So the mass of MnF3 will be the molar mass. You have to multiply by the molar mass. So 19 into 3, MnF3 19 into 3 plus 55. Right? Mass of MnF3. Grams. Multiplied by 0.1 moles. So 9 into 3, 27. 9, 3, 27, 2 remaining, 3 into 1, 3, 4, 5 plus 55 multiplied by 0.1. So that's going to be 112, right? 112 into 0.1, that's 11.2 grams, right? 11.2 grams. They're asking what? Is the percentage yield, what is the mass of MnF3 obtained when 0.1 more? They are asking the obtained mass, right? So obtained mass, now theoretical mass is 11.2, so 80% multiplied by 11.2 will be the answer, right? 80% of 11.2 is going to be your answer. So 0.8 multiplied by 11.2. That's 8.96. That's answer number 3, right? 11.96 answer number 3. Right. So 5th done. Next we are going on to the 20th. Sorry, not 20th. Sorry, my bad. 7th one. I saw this one and I told 20. Right. Let's take this. Enthalpy change, delta H for the dissolution of sodium hydroxide in water at the temperature 23 degrees Celsius is minus 42 kilojoules per mole. Right, and amount of 20 grams of sodium hydroxide solid was dissolved in 230 grams of water at 27 degrees Celsius in an insulated container. The specific heat capacity of the solution is 4.2. What is the final temperature of the solution? Okay. Now here, 20 grams of sodium hydroxide is reacted with water. Now water is 230 grams low. First of all, let's calculate the number of moles of each to find the limiting region. Now who is going to react and finish first? Right? Number of moles of sodium hydroxide will be 20 grams divided by 23. So sodium is 23 plus 16 plus 1 grams per mole. Right? So if we calculate that, here then 24 and 40, right? So that's going to be 0.5. Number of moles of water, on the other hand, 30 grams divided by 16, 17, 18. 18 grams per mole. Okay, 230 divided by 18. 12.77. That's a large amount of moles. So actually the limiting reagent will be sodium hydroxide, of course. They have told the temperature change and everything we have to find, right? Okay. Now let's calculate the heat change that has occurred. If we know the enthalpy change, which is minus 42 kilojoules per mole, multiplied by the number of moles reacted, 0.5 moles, you're going to get the heat change, right? So heat change, 5 into 2, 10, 1 remaining, 5 for 20, 21. 21.0 kilojoules. That's the amount of heat change that has occurred. Then the next one is we have to calculate the temperature change. Now you apply delta Q is equal to dVs delta theta. Right? So delta Q will be 21 10 to the power 3 joules. Right? 21 10 to the power 3 joules is equal to the density. Where's the density? They haven't given it. The specific heat capacity, and they have given the mass, right? We can take it from the mass without taking the density. We'll take it like this. The total mass only we have to consider then ms delta theta. So the total mass of the system, 20 grams and 230 grams, that's going to be how much? 250 grams. 250 grams multiplied by specific heat capacity, 4.2 joule per gram per Kelvin, right? 4.2 joule per gram per Kelvin. That's going to be the specific heat capacity. Then the temperature change will be final minus initial. Since this is an exothermic reaction, because it has a minus 42, that means temperature should increase. So theta minus 23, I'll put here. Right? So when you simplify everything, Lamai, 21 divided by 250 divided by 4.2. That's 0.02 into 10 to the power 3. That's 20, right? Theta minus 23 is equal to 20. Theta is equal to 43. Isn't that easy? Isn't that easy? Huh? Isn't that easy? Like, seriously. That should be easy, right? I mean, we are just applying the basic concepts of enthalpy. We have done this in the energetics class also, these kind of MCQs. So, very easy. And all you have to do is follow these steps. You calculate the heat change and then apply into the equation. Since they haven't given the density and volume, we apply mass. So that's how you get the answer there. Right, let's go for the 8th one and 9th one. Okay, 8th one, let's do. A volume of 25 cubic centimeters or 0.02 mole per cubic decimeter KiO3, right? IO3 minus reacting with I minus reaction they are talking about. Right, I told you how to balance this reaction, right? We put 2 and 2, 3 into 2, 6, and plus 12 and plus 10. Here minus 2, here 0, here 0, here 2, here 10. So 2 into 5, that's going to be 10 here, and then 5 here. So you add them together, IO3 minus plus 5I minus goes to 6I2. Then you balance the charges, it's going to be 6H plus on the left hand side. In order to balance that, we put 3H2O on the right hand side. Remember, balance can hattie, I won't teach you now. That's chemical calculations. KO3 reacted with the solution was acidified and 15 cubic centimeters, 0.5 mole per cubic decimeter Ki solution was added. The liberated additive was titrated with this Na2H2O3 solution using starch as indicated. The volume of the thiosulfate solution required for titration was 20 cubic centimeters. The concentration of sodium thiosulfate in the solution is in mole per cubic decimeter. So first of all, we have to calculate the moles of these both, right? Number of moles of IO3 minus, number of moles of I minus, and we have to calculate the limiting reagent. So number of moles of IO3 minus will be 25 10 to the power minus 3 cubic decimeters multiplied by 0.02 mole per cubic decimeter. So per cubic decimeter cancels off. That's going to be 25 into 2, 10. That's 25 into 2, 50. So 0.5 moles. 0.5 moles will be the number of moles of iO3 minus. Right? Then number of moles of I minus will be 15 10 to the power minus 3. Cubic decimeters multiplied by 0.5 mole per cubic decimeter. Right, 5 into 5, 25, 2 remaining, 5 into 1, 5, 6, 7, 7.5, 10 to the power minus 3 moles. 0.5, 10 to the power minus 3. Yeah, 10 to the power minus 3. Right, so the limiting reagent, of course, in this case will be iO3 minus, right? The number of moles of I2 formed will be 0.5, 10 to the power minus 3 multiplied by 6 over, and this will be 3, right? Not 6. 5i minus, yeah, 3, right? 6 remain, this should be 3. 3 over 5, right? 3 over 5. That's going to be 0.3 into 10 to the power minus 3 moles. That's the number of moles of I2. Right, now the liberated I2 was titrated with S2O32 minus using starch as indicator. The volume of S2O32 minus required, right? The volume of S2O32 minus required for the titration was 20 cubic centimeters, right? Now from I2 we can calculate the S2O32 minus amount, because I2 will react with S2O32 minus according to this equation. 2S2O32 minus forms S4O62 minus and I minus, 2I minus actually. Then the number of moles of S2O32 minus will be twice that amount, right? 0.6 10 to the power minus 3. Right? 0.6 10 to the power minus 3 moles. Then the volume of S2O32 minus consumed will be 0.6 10 to the power, not the volume, they're asking concentration, right? So the concentration will be 0.6 10 to the power minus 3 moles. You divide that by the volume, 20 into 10 to the power minus 3 cubic decimeters. So 0.03 mole per cubic decimeter. So there you go. 0.03 mole per cubic decimeter will be the concentration. I think there's a small calculation error somewhere. So here the volume and the concentration 0.02, 25 into 250. Going to be 0.5 10 to the power minus 3 moles. Then here I minus 15 into 0.5, that's going to be 7.5 10 to the power minus 3. And the limiting reagent 1 and 3, 1.3. The number of moles of I2 formed will be from 0.5 10 to the power minus 3 multiplied by 3 divided by, that's wrong. You can't divide by 5 again because that's for I minus. I'm taking the limiting reagent as IO3 minus. So therefore it's going to be 3 times. That's going to be 1.5 10 to the power minus 3 moles. Right? 1.5 10 to the power minus 3 moles. So 1.5 10 to the power minus 3 moles, you multiply by 2. That's going to be 3 10 to the power minus 3 moles. Right? So after that, you can divide by the volume. Right? 3 divided by 20 mole per cubic decimeter. That's 0.15. So 0.15 mole per cubic decimeter will be the answer. That's answer number 5. Right, there you go. Right, let's go for the question number 9 then. Calcium carbonate and aluminium carbonate undergo thermal decomposition as given below. How much of carbon dioxide is formed from aluminium carbonate when 3.34 grams of equimolar mixture of calcium carbonate and aluminium carbonate is thermally decomposed? Okay, now first of all, what I'm going to do is I'm going to put X into the mass of aluminium carbonate. Mass of Al2CO3 3. I'm going to put it as X, right? So the mass of calcium carbonate, on the other hand, will be 100. Sorry, not 100. 3.34 minus X. So that's going to be the mass of calcium carbonate. Then they have told the number of moles are equal, right? So this one should be equal to this one. So number of moles of calcium carbonate equals number of moles of aluminium carbonate, Al2CO3 3. So that's going to be mass over molar mass. So X over 234. X over 234 will be equal to, X over 234 is equal to 3.34 minus X divided by 100. So 100X is equal to 234 multiplied by 3.34 minus 234X, right? So 234X is going to be 334X equals 234 multiplied by 3.34. So when you simplify this, 3.34 multiplied by 234, that's going to be 781.56. You divide that by 334. That's going to be 2.34. X is equal to 2.34. Right? X is 2.34 grams. So what is that? The mass of aluminium carbonate. So from the mass of aluminium carbonate, I'm going to calculate the number of moles of aluminium carbonate. That's going to be 2.34 grams divided by 234 grams per mole. Very easy, right? 0.01 moles. So that's the number of moles of aluminium carbonate. From number of moles of aluminium carbonate, you can find the number of moles of carbon dioxide from aluminium carbonate by using the stoichiometric ratio. And that's going to be how much? That's going to be 3 times, right? 3 times. So 0.01 multiplied by 3, that's 0.03 moles. Then the mass of carbon dioxide formed 0.03 moles multiplied by 44 grams per mole. 3 into 4, 12, 1 remaining, 3 into 4, 12 plus 1, 13. 1.32 grams will be the answer. So there you go. With that, the missile paper, sorry, not missile paper, what do you call me? Yeah, missile paper number 4 will be over with that, right? So with that, the missile paper number 4 is complete. So let's get ready for the missile paper number 5.